Dear students, under the topic graph theory, here we have a very significant theorem. Let capital G be a P, Q graph, which means G has P number of vertices or also known as points and Q number of edges also known as lines. The following statements are equivalent. So we have to prove that these statements are equivalent to one another. The first statement is G is a tree, followed by every 2 points of G are joined by a unique path. And the third statement is G is connected and P is equal to Q plus 1. And then we have G is acyclic and P is equal to Q plus 1. So if we want to prove that these statements are equivalent, then it is sufficient to prove that 1 implies 2 and then 2 implies 3. 3 implies 4 and finally 4 implies 1. So if we prove in this order, we will be proving that all the statements are equivalent. So what we have to prove is, first we have to assume 1 and we have to prove 2. And assuming 2, we have to prove 3. And assuming 3, we have to prove 4. And finally, assuming 4, that is the statement 4, we have to prove the statement 1. This is the method of proof whenever we have to prove that the following statements are equivalent. So as the first step, we shall write what is given for us. It is given that G is a P, Q graph. That is, G has P points and Q lines. So let us write that. So we have written that P points also refers vertices and lines refers edges. So now next is we have to assume the statement 1 and we have to prove the statement 2. That is, to prove, we have to prove that 1 implies 2. So this is our first step in proving. So we have to assume 1 and we have to prove 2. So in order to assume 1, what is statement 1? G is a tree. So we have to assume that G is a tree. So first we have to take let capital G be a tree. So by the definition of tree, we know that a connected acyclic graph is known as tree. So it implies that. So capital G is a tree implies that G is a connected acyclic graph because we know that tree is the connected acyclic graph. So let us write that. So we have taken statement 1 and we have assumed it. Next we have to prove statement 2. That is, we have to prove that every 2 points of G are joined by a unique path. So let us write that. So we have written, that is, to prove that every 2 points of G are joined by a unique path. Now in order to prove this, we shall consider two vertices of the graph G. That is, we are going to take two vertices U and V of the graph G. So we have taken two vertices. So any two vertices U and V of a graph G. Now we know that since G is a tree, it is a connected graph. So by the definition of connectedness, we know that in a connected graph, exists at least one path between every pair of vertices. So if we have a connected graph, in that connected graph, there will exist at least one path between every pair of vertices. This is by the definition of connected graph. So we shall take and write that. So now G is connected. So we have taken two vertices U and V from G. Then by the definition of connectedness, there will be a path between these two vertices and there will be at least one path. So we can take that there exists a UV path in G. So if we take like that, now since G is connected, because we have taken G to be tree and we have got that G is connected. Now since G is connected, there exists a UV path in G. Now what we have to prove? We have to prove that this path is unique. So that is what we have to prove. So now since G is connected, there exists a UV path in G. Now we have to prove that this UV path is unique. So that is what I have written. So we have to prove that this UV path is unique. So first we have assumed one, that is G is a tree, and since G is a tree, it is a connected acyclic graph. Then we have to prove 2. So what is 2? We have to prove that every 2 points of G are joined by a unique path. So for that we are considering 2 points U and V of G. Now, by the definition of connectedness, if you have a graph G and if there are 2 points, then definitely there will exist at least one path between every pair of vertices. Now, since G is connected, here also we have taken 2 vertices U and V, and so there will be a UV path. This UV path, we have to prove that it is unique. So that is what I have written. Now, unique means what? Unique means there exists only one path of that type. You cannot find another path between the vertices U and V. So, there will exist only one unique path. So, only one. So, that is what we have to prove. In order to prove this, we are going to prove this by the method of contradiction. We want to prove that there exists only one path. So for contradiction, we will assume that there exists another path, that is there exists two paths, and we will prove that our assumption is wrong. So this is the method of proof. So since we want to prove that UV path is unique, that is there exists only one path of this kind, we will assume the contradiction that there exists another path also, and we will prove that our assumption is wrong, that is it contradicts. So this is how we are going to prove. So I have taken and written that we are going to prove this by the method of contradiction. So if we want to prove that it is unique, let us assume the contradiction. So let us assume the contradiction that there exist two distinct UV paths in the graph G. So let us assume that there exist two distinct. Since we want to prove it is unique, we are assuming the contradiction that there exist two distinct UV paths in G. So those two distinct UV paths we are going to take as P1 and P2. So path P1, how we are going to take, the starting point is U, which we can also take as V0. Then followed by the vertex V1, then V2. So we are traveling like this and we are reaching a point Vn, which is V actually. So the initial point is U and the final point is V. So this is one path. So this is how we are traveling. So V0 to V1, V1 to V2, etc. and we are reaching Vn. And we are going to consider another path also. So P2, let it be another path. So it will start from U and that path be W0, W1, W2. So two distinct paths they are, Wn, and the final point is V. So it is starting from U and ending at V. And this is one path and this is another path. So two distinct paths we are taking. So how will be the union of these two paths? The union of these two paths is P1 union P2, which will be either a cycle. So the union of these two will be either a cycle or it will contain a cycle. So let me show that with the help of an example. See, we are having 2 points. This is point U and this is point V. So now I am going to take a path. So suppose I am taking this path. So U2, V1, V2, V3. It goes like that up to Vn somewhere. And then, this is Vn. So it has reached here. This is path P1. Now again from this U, we are having another one path to V. How? That is, this is W0 and then W1, W2, W3. It keeps on going like that. So here also it keeps on going. It's like that. Somewhere Wn minus 1 and Wn, which is V. So this is one path P1 and this is path P2. So if you see, it forms a cycle. So it will be either a cycle or how it can be, you can have it like this. So if you have a vertex U, so this is U. Now we are going to reach V with two different paths, and how those paths are going to be. For example, if I am going like this and then like this, another point. So I'm just traveling and I am reaching this V. So let this be path P1. And then I can travel like this, and there to this point, and this point, and I'm reaching here. So if you see, this is another path to reach from U to V, which is P2. So this is path P1, as you can see, and this is path P2. So it contains cycle. So if you see here, there is a cycle, and here also there is a cycle. So here it was fully a cycle. So it can be either a cycle, or it can be like this. It can contain cycle. So from this we can say that, so we can say that G contains a cycle. But it is a contradiction because G is a tree, and in a tree you cannot have a cycle. So contradicting the fact that G is acyclic. So if we know that G is acyclic because G is a tree by our assumption. So what is a tree? A tree is a connected acyclic graph. So acyclic means it should not contain a cycle. But we took two paths and we got that G is a cycle, which is a contradiction. Therefore, our assumption that there exist two different distinct paths is not true. So what happens because of this contradiction? We can say that there will exist only one unique path. So hence there exists a unique path. That is what we wanted to prove. Because one, we assumed that it is a tree, and we have to prove that every 2 points of G are joined by a unique path. So that we have proved. So that is what we have proved. Therefore, we have proved that 1 implies 2. So hence 1 implies 2 is proved. So next step is what? We have to prove that 2 implies 3. That is, we have to assume the statement 2 and we have to prove the statement 3. So by the method of proof, because that is the method of proof. Already I told you. So 1 implies 2 is done. Next is 2 implies 3. So I have written, next we have to prove that 2 implies 3, for which we have to assume 2. So what is 2? Every 2 points of G are joined by a unique path. So first let us write that. So we have taken and written. Now we have to prove that is third one we have to prove. 2 implies 3. That is, we have to prove that G is connected. One thing. And second thing, we have to prove that P is equal to Q plus 1. That is, the number of vertices is equal to number of edges plus 1. So in order to prove this, if you see, we have assumed that every 2 points of G are joined by a unique path. By the definition of connectedness, we know that, so by the connected graph, what do we know? There exists at least one path between every pair of vertices. So if we know that there exists at least one path between every pair of vertices, we can say that the graph is connected. Now here we have assumed that every 2 points of G be joined by a unique path. So this will imply, since there is a path between any 2 points of G, okay, there is every 2 points of G, we can say that G is connected. So from this, we have proved one of the required result, that is G is connected. So this is proved. The remaining part is P is equal to Q plus 1. So we have to prove this. In order to prove this, we are going to prove it by the method of induction on the number of vertices. So let us see the proof. So what we are left out to be proved, that is to prove that P is equal to Q plus 1. So which we are going to prove by the method of induction on the vertices P. So by the method of induction on the vertices P, we are going to prove this. The result is obvious for P is equal to 1. So for now we will take when P is equal to 2. So if P is equal to 2, then what will happen to G? We know that P is equal to 2 means the number of vertices is 2. So in order to keep it a connected graph, because we have proved that it is a connected graph, definitely there should be an edge between these two vertices. So there will be only one edge. So we see that this is a graph K2. So G will be equal to K2. So how many edges are there? Q is equal to 1. So from this we can say that q is equal to 1. So which implies, what is q plus 1? It is equal to 1 plus 1, which is 2, and that is equal to p. Therefore we have proved that p is equal to q plus 1 in this case. So it is done. So we are done with the proof in this case. So hence p is equal to q plus 1 in this case. Next we have to assume this result is true for graphs lesser than p points, because we are proving by the method of induction. So if you have a graph G with lesser than p points, then the result is true. This is our assumption. So you should remember this. With this assumption, we are going to prove further. So now first we will consider a graph G with p points. So after taking a graph G with p points, what we will do, we will take an edge. And let us represent that edge as x, which is equal to uv. So because we have two vertices uv in G, and the edge joining these two vertices uv is taken as x. And so it is written as x is equal to uv. So this be any edge in G. So let it be any edge in the graph G. Okay, in our theorem we have taken, if you have any 2 points in G, then it will be joined by a unique path. Now we have taken a point U and V. So there will be a unique path between U and V. So if you remove that one path from the graph G, so if you remove this edge, the graph will become disconnected, and it will be disconnected into two components. So let us take those two components as G1 and G2. So let me put that in words. So I have written here, since there exists a unique path uv in G, and since it is a path, if you remove it, so if you remove this edge x from G, it will become disconnected with exactly two components. Now let me show this with the help of an illustration. So let me just randomly take a graph G. So for example, if I have taken a graph G, which is a connected graph, so there is an edge between U and V. So let me just extend the graphs for your better understanding. So I have just taken randomly a graph. So this is a graph that we are just randomly considering. So if I am considering this as graph G, now this edge UV is X. What I'm going to do, I'm going to remove this edge, this one edge from the graph G. So I'm going to obtain a graph G minus X. So how will it be? So I am going to remove this one edge. So this edge I am going to remove. So if I am going to remove, this vertex and this vertex will remain. They will not go away. Only the edge is removed. So how the graph changes? Now since this edge is removed, there will be no edge between U and V. So this is U, this is V that I have drawn. But the remaining graphs will be as it is, because there exist. So if you see, these remain as it is. Similarly here, the remaining graph will be there as it is. But the graph has got disconnected because I have removed one edge. So it has been disconnected into two different graphs. So let me take this one graph, that is one component, as G1 and this component as G2. So that is what we are saying. I hope now you would have understood. Since there exists a unique path uv in graph G, G minus x, so this graph is G minus x, is a disconnected graph. So it is disconnected with exactly two components, G1 and G2. So that is what we have said. We know that this G is acyclic. So since G is acyclic, what about G1 and G2? These are the components obtained from G. Even they will be acyclic. So since G is acyclic, both the components that we have obtained from G, that is both G1 and G2, even they will be acyclic. So are acyclic. So now since they are two different components, we have represented it as G1 and G2, and since G is acyclic, though these components G1 and G2 are also acyclic. Now this is one separate graph and this is one separate graph. So it will have its own vertices and edges, and this also will have its own vertices and edges. So let us take the vertices and edges of G1 as P1, Q1, and the vertices and edges of G2 as P2 comma Q2. So let me write that. So I have written that. So G1 be a P1 comma Q1 graph and G2 be a P2 comma Q2 graph. Joining these two graphs only, we have the graph G. So we can say that the total number of vertices P will be equal to P1 plus P2, because the vertices of G1 plus the vertices of G2 will give us the vertices of G. Therefore, P, that is the vertices of G, will be equal to P1 plus P2. What about Q? The edges of G, it will be the edges of G1 plus the edges of G2 and the edge that we have removed. How many edges we removed? We removed only one edge. So plus that one will give us the edges of G. I hope you would have understood this. Next, we will further to prove this theorem by the method of induction hypothesis. So further, by induction hypothesis, what we have assumed, we have taken that the result is true for graphs with lesser than p points. So now if it is true, we know that G1 is a graph with P1 points which is lesser than P. Similarly, G2 is a graph with P2 points which is lesser than P. And so the theorem is true, that is P is equal to Q plus 1 is true for P1 and P2. So what will happen if it is true for P1? P1 will be equal to Q1 plus 1. Similarly, P2 will be equal to Q2 plus 1. So the theorem is true for these two components. So let us write that. So since the theorem is true for them, P1 is equal to Q1 plus 1 and P2 will be equal to Q2 plus 1. Now, for using this, we can write. So hence, now we know that P is equal to what? P1 plus P2, which is equal to, what is P1? It is Q1 plus 1. And what is P2? Plus Q2 plus 1. Let us just rewrite it. So this will be equal to Q1 plus Q2 plus 1 plus this one. Now what is this? This is equal to Q. So this is equal to Q plus 1. That is because of this that we have taken. Because Q is Q1 plus Q2 plus 1, and since P is equal to P1 plus P2, we took this, and substituting P1 and P2, we have obtained this one. That is Q plus 1. So therefore we have proved that P is equal to Q plus 1, which is what we wanted to prove. That is, we wanted to prove that P is equal to Q plus 1. Already we have proved that G is connected, and now we have proved that P is equal to Q plus 1. So therefore, assuming 2, that is every 2 points of G are joined by a unique path, we have proved 3, that is G is connected, which we proved in the beginning of the theorem, beginning of the proof of 2 to 1. And now we have proved that P is equal to Q plus 1, and therefore we have proved. So hence 2 implies 3 is proved. Next, the next part of the proof is 3 implies 4. So if you see, first we proved that 1 implies 2, and now we have proved that 2 implies 3, and now the next part of the proof is 3 implies 4. So let us prove that. Now in order to prove that 3 implies 4, we have to assume 3 first. That is, we have to assume that G is connected and P is equal to Q plus 1. And using this, we have to prove that G is acyclic and P equal to Q plus 1. This P equal to Q plus 1 is already there in 3. So obviously it will be applicable for 4. So no need to prove this one. But we have to prove that G is acyclic. So this is what we have to prove. So this is the only proof that we have to do. So let us do that. So now by 3, G is connected and P is equal to Q plus 1. So the only thing that is left out is to prove that G is acyclic. So to prove G is acyclic. Now in order to prove G is acyclic, we are going to assume the contradiction. We are going to assume that G contains a cycle. So actually acyclic is G does not contain a cycle. That is what it means. So we are going to assume the contradiction in order to prove that G is acyclic. So what is the contradiction? Let us assume the contradiction that suppose G is not acyclic. So that will imply G contains a cycle. So G contains a cycle. So let us take the length of this cycle as n. So let us take that G contains a cycle of length n. So n is the length of the cycle, which means the cycle will have n number of vertices as well as n number of edges. So there are n points, that is vertices, and n lines, so n edges on the cycle. Now let us fix a point u on the cycle. So we know that there are n points and n lines on the cycle. Let us fix a point u. So let us take it. Now after fixing a point u on the cycle, we shall consider any one of the remaining p minus n points which is not on the cycle. Now we know that G is a graph. For example, if you have a graph like this. So this is a cycle and there are some more points in the graph. Okay. So this is the total graph with p points. The number of points on the cycle is alone n, and we are fixing one point u in this cycle on this cycle. What about these points? These are the remaining points which are p minus n points. Totally we have p points. There is a cycle in this graph G which has n points on it. We are fixing one point u on it. And what about the remaining points? It will be p minus n. So except the points on the cycle, the remaining points will be p minus n. So we are considering any one point of the remaining p minus n points. For example, if this one point which is v, so that is only v which is not on the cycle. See, it is not on the cycle. So now this point v we are considering. We know that there will be a path. Now it's like this. So there will be a path from u to v. So from u to v there will be a path, because since G is connected, we can find a path, and we can in fact find the shortest path from u to v. So let me write that. So now since I have written that here, and since G is connected, we can find a shortest path from u to v. Now consider a line which is incident. Okay, consider a line which is incident with v in this shortest path. We are considering a line which is incident with v. Now what about the p minus n lines? It will all be distinct. So they are all distinct. So now since they are all distinct, what we will have? We will have q, that is the total number of edges, to be either greater than or equal to the number of lines which is not on the cycle plus the number of lines on the cycle, which will be equal to p. So which is a contradiction, because we are getting q is greater than or equal to p, but we know that q plus 1 is equal to p, which means that q is not greater than p, because we get q as to be equal to p minus 1. So that implies that q is not greater than p, and this case is not true. Now since this is not true, our assumption that G is acyclic cannot be true. Our assumption that G is cyclic, because we wanted to prove that G is acyclic, we assumed here. Suppose G is not acyclic is not true, and therefore G is cyclic. So hence we have proved the required result. So thus G cannot contain a cycle, which implies G is acyclic, which is what we wanted to prove. That is, we assumed 3 and we have proved 4. So this is done. Now finally we are done with 3 to 4 also. Finally we have to prove 4 to 1. So we have to assume that G is acyclic and p equal to q plus 1, and we have to prove that G is a tree, that is 1. So let us see the proof. So therefore we are done in proving 3 to 4. Now final part, that is we have to prove 4 implies 1. What is 4? 4 says that the statement 4 says that G is cyclic and p is equal to q plus 1. So let us write that. That is, G is acyclic. Okay, so G is acyclic and P is equal to Q plus 1. We have assumed this. Now we have to prove one, that is, we have to prove that G is a tree. So now we have to prove that G is a tree. But by the definition of tree, what do we know? What is a tree? A connected acyclic graph is a tree. A connected acyclic graph is a tree. But already we have taken that G is acyclic. So this is done. So we have to only prove that G is connected. So if we prove that G is connected, we are done with the proof, because already it is acyclic. So let us prove that G is connected. And when do you say that a graph is connected? So by definition, we say that it is a connected graph if there exists at least one path between every pair of vertices. So this is what we have to prove. Now in order to prove it is connected, we are going to prove it by the method of contradiction. We are going to assume that G is not connected. So we are assuming the contradiction that G is not connected. So not connected means what? G is disconnected. So we have assumed that G is disconnected. So disconnected means it will have more components in it. So let us take those components as G1, G2, G3, etc. We will take K components. So let G have K components. So let it be disconnected into K components, where we can say that K is greater than or equal to 2. So minimum it will be 2 components or more than 2. So let us take those components as G1, G2, G3, etc. up to Gk be the components of G for K greater than or equal to 2. So now what? G is acyclic already. So if G is acyclic, what about the components of G? They all will be acyclic. So in fact they will be tree. And since G is acyclic, each of these components is a tree. And now what about the edges of G? The edges of G, that is, the number of edges of G will be equal to the total number of, equal to 1 to K, because there are K components. Total number of edges of each components. We can add the number of edges of each of the components. So what is Q actually? Q is equal to, if it is G1, the number of edges will be Q1. G2, the number of edges will be Q2. G3 will have number of edges as Q3 and etc. And finally you have graph GK with number of edges as QK. But we know that from assumption that P is equal to Q plus 1, which means that P1 will be equal to Q1 plus 1, P2 will be equal to Q2 plus 1, etc. Pk will be equal to Qk plus 1. So from this we obtain Q1 as what? P1, actually Q1 is equal to P1 minus 1. So taking this 1 to the other side. Similarly, Q2 will be P2 minus 1. Qk will be Pk minus 1. So let us substitute that over here. So Q will be equal to, what is Q1? P1 minus 1. So P1 minus 1 plus Q2 is P2 minus 1 plus Q3 is P3 minus 1, etc. Finally, we have Qk as Pk minus 1. Now let us gather the terms. That is, all the P terms we will gather. So it will be P1 plus P2 plus P3 plus etc. up to Pk. And all the ones we will gather. So how many ones we will have? We will have K ones, because we have added till K terms. This negative sign we will take common throughout, and 1 plus 1 plus 1 plus you have until K times. And so therefore that will be equal to, what about P1 plus P2 plus P3 plus Pk? It is the number of vertices P minus, if you add 1 K times, it will be 1 into K. So that will be K. So P minus K. We obtain Q to be equal to P minus K, which implies P is equal to, if you take it to the other side, it will be Q plus K. But for K greater than or equal to 2. But this is a contradiction. because we know that P is equal to Q plus 1. So, because of this contradiction, P cannot be equal to Q plus K, and therefore, since P is equal to Q plus 1, it becomes a contradiction, and therefore, our assumption that G is disconnected is not true, and hence G has to be connected. Because if we assume the contradiction G is disconnected, we are arriving at a contradiction that P is equal to Q plus 1, which is against the fact that P is equal to, P equal to Q plus K we get, which is against the fact that P is equal to Q plus 1. Therefore, our assumption that D is disconnected is wrong, and hence G has to be connected. So, which is a contradiction since P equal to Q plus 1, and hence G cannot be disconnected, and therefore G has to be connected. And already G is acyclic, therefore a connected acyclic graph is a tree, so which implies capital G is a tree, which is what we wanted to prove. So we wanted to prove that G is a tree, and so we are done with it. So hence we have proved that G is a tree, and hence 4 implies 1 is proved. So hence 4 implies 1 is proved, and this proves the whole theorem, because we started with proving 1 to 2, 2 to 3, 3 to 4, and finally 4 to 1 is also proved, and hence we have proved that all the statements are equivalent. The following 4 statements are equivalent to one another. So hence this proves the theorem. So if you go through one by one patiently, definitely you will understand. So the theorem was to prove that these 4 statements are equivalent. First we assumed assumed 1, and we proved 2, and then we assumed 2, and then we proved 3, and after that we assumed, if you see, we assumed 3 and we have proved 4, and finally we have assumed 4 and we have proved 1. So with this we are done with the proof of the complete theorem. This is a very significant 15-mark question in the examination point of view. Thank you.